In today's class, I wanted to continue our work on solving partial differential equations numerically. In the last class, we examined Laplace's equation from electrostatics, and we solved that numerically using a method that's called the relaxation method. In today's class, I want to examine the heat or diffusion equation. We're going to solve that numerically. We're going to solve it using what's called the leapfrog method, and we're going to look at examples from thermodynamics. Before discussing the heat equation, I wanted to say a few words about heat conduction as a background to the heat equation. So, an important question, interesting question, one that's not always asked in a thermodynamics class is, at what rate does heat flow from a hot object to a cold object? How long does it take a hot object to cool down? How long does it take a cold object to warm up? So, to answer this question, first, let me just mention different ways, different mechanisms for the transfer of heat, for the transfer of energy. So if I had an object in empty space, then the heat transfer to or from that object would be by radiation. If I had a liquid, a gas, the heat transfer from within that liquid gas is often by convection. So an example is the Earth's atmosphere, where convection dominates the flow transfer of heat. The ocean, where convection dominates the transfer, the flow of heat. But in solids, heat is transferred by collisions. Heat is transferred by conduction. So heat is transferred in solids by the collisions of the electrons with other electrons, ions with other ions. So for example, fast electrons colliding with slow electrons will transfer energy, which becomes the transfer of heat. Fast ions colliding with slow ions will transfer energy, which becomes the transfer of heat. Now, in a material like a metal, where there are free electrons, then it's typically those free electrons that are responsible for heat transfer. And in metals, thermal conductivity tends to be high. On the other hand, in insulators, it's typically the lattice ions that are responsible for heat transfer. And typically in insulators, the thermal conductivity is quite low. The equation that governs the transfer of heat and determines the rate of heat transfer is the equation we call the heat equation. I've denoted it down here. It's a partial differential equation with differentials with respect to space and time. It's a partial differential equation for the temperature of the solid as a function of space and time coordinates. And it incorporates a constant, a coefficient between the time and space derivatives. It's called the diffusion constant. I've given it the symbol D here. And that diffusion constant sort of sets the scale for heat transfer. If that diffusion constant is large, then heat transfer is rapid. If that diffusion constant is small, then heat transfer is slow. If that diffusion constant was 0, then there would be no heat transfer. So on the next 4 slides, I've got 2 slides about a theoretical solution to Laplace's equation. It's a reminder from last class. And then I've got 2 slides on the theoretical solution of the heat equation. And that's something new that we're going to compare to the last class. So I'm going to start with a reminder. I'm just going to outline how we solved theoretically Laplace's equation using separation of variables. And then I'm going to outline how we solved theoretically the heat equation using separation of variables. And when we look through the Laplacian reminder, when we look through the heat equation introduction, you probably want to be thinking about the similarities between these 2 examples and the differences between these 2 examples. So similarities are we're solving partial differential equations by separation of variables using boundary conditions, initial conditions. Differences are, for example, one's from the world of electrostatics and another one's from the world of thermodynamics, so that they're physically different. But we'll see that mathematically, the solutions to the 2 problems, one from electrostatics and one from thermodynamics that I'm presenting, are really very similar. So let's start with Laplace's equation. And on this slide here, you see an example problem in electrostatics. That's over on the left-hand side. We've got a region of space inside the box where we want to figure out the potential. And then we got boundaries to that region of space where we know the potential. We've got a conducting plate at the bottom here at a fixed non-zero potential. And then we got grounded plates on the left and right at 0 volts. And then far away from the arrangement, upstairs here, we've also got 0 volts. And we want the potential inside. So to solve this analytically, to solve this theoretically, we would start with Laplace's equation. And we would apply separation of variables to Laplace's equation. That turns it from a partial differential equation into a set of ordinary differential equations. Then we would work with the solution, the general solution to those differential equations, and we would tailor that general solution to the differential equations to the specific boundary conditions of our problem. So let me just, on the right-hand side here, walk through those steps. Upstairs here, first equation. This is Laplace's equation in 2 dimensions for the electrostatic potential. It says that the second-order partial derivative of the potential with respect to our x plus the second-order partial differential of the potential with respect to y, sum to 0. It's saying, if you think about differentials, second-order differentials as representing curvature, the curvatures of the potentials in x, curvatures in the potentials in y are related and sum to 0. So the procedure for solving this is to break this single partial differential equation down into a pair of ordinary differential equations. The assumption in this step, the hypothesis in this step, is that we can replace the electrostatic potential phi with a product of 2 functions, one only of x, I called it uppercase x, one only of y, I called it uppercase y, and make that assumption, make that hypothesis, and in that way, break the partial differential equation down into a pair of ordinary differential equations. So I replaced phi with x times y. I plugged that in, and that allows you to pull this partial differential equation into 2 halves. One half only depends on the function of x. The other half only depends on the function of y. And those 2 halves have to be equal and opposite. And if they're equal and opposite, I can assign their values to be equal to some constant. I called it beta squared here. And so that's the procedure for decomposing the partial differential equation into two ordinary differential equations. And here they are. Now, these are familiar ordinary differential equations. If you look at those two equations, they say that the second order differential of some function, x or y, is in proportion to the function itself, x or y. And there's a proportionality constant. And so we can write down the general solution to the electrostatic potential in Laplace's equation as a product of the general solutions to the ordinary differential equation for x, the ordinary differential equation for y. And that's all I did in this third equation here. This is just me recognizing, spotting the general solution that has emerged from this separation of variables and taking the partial differential equation into a pair of ordinary differential equations. And it has this form here. So if you look at this form, it's a function of x and y, of course. It has this parameter, beta, that emerged when I separated the variables. And beta could take any value. And then it has another number of other coefficients, A1, A2, B1, B2, which would be determined by your particular problem, which in this general solution just define a enormous infinite set of solutions that there are to that partial differential equation. The next step then is applying the boundary conditions. The boundary conditions on the bottom of the plate, the left, right of the plate, the top of the region of space. And if you apply those boundary conditions, I'm not describing any details of doing that, out of this general set of solutions with all these parameters, A1, A2, B1, B2, and beta, emerge a single solution. And I've written this down here. So this is the solution to our particular problem. Let me make a few comments about it. It's a function of x and y. So it tells us how the potential varies inside the box as a function of x and y. It's dependent on the potential that's applied to the lower plate. The other regions, bounding regions, are at 0 volts. So it's a function of phi naught. The functions of y and the functions of x that are in this solution are, for y, there's this single multiplying negative exponential that causes the potential to fall off as you walk vertically up the region of space. And then there's this summation of sine waves, summation over odd values of n, making a superposition of sine waves that determines the x dependence of the electrostatic potential. And it's this superposition of sine waves that ensures that the potential over here on the left-hand side and over here on the right-hand side are 0. So this is how we arrange for the boundary conditions. You'll notice that the variation in y and the variation in x are linked to one another because, for example, n is present in both the sine function here and the exponential function here that contain the x and the y dependencies. So this plot shows the solution, or depicts the solution to that problem involving Laplace's equation, depicts the electrostatic potential in that region bounded by the metal plates. Horizontally, I'm plotting the position. So from the left-hand side of the box to the right-hand side of the box. And vertically, I'm plotting the electrostatic potential. And I've imagined that I've put 1 volt on the lower plate of the box. So phi naught is 1 volt. And then these different lines, the red line, the green line, blue, yellow, magenta, azure, these are the potentials, the profiles of the potentials in X at different heights in the box. So at a height of 0, which is where the bottom plate is located, that's the red line, a height of 1, that's just above the bottom plate, and then 5, 10, 15, 20, walking up and up towards the ceiling of the box. And so on the bottom plate, you see the potential is 1 volt everywhere. That was our boundary condition. On the first step above the bottom plate, you see that the potential has fallen off a bit at the center. It's fallen off a lot on the extremes on the left and right, because the potential is forced to be 0 on the far left and the far right due to the boundary conditions of the metal plates on the far left and the right. And then as you see, as you walk higher and higher and higher up the box, y equals 5, 10, 15, 20, you see the potential decreasing and decreasing as we move towards a potential that ultimately will be 0 when we're way above the floor of the box, the bottom of the box. And so this is a picture, this is a depiction of that particular solution we have theoretically derived. So now I want to talk about theoretical solution of the heat equation by separation of variables. As I say, we're going to compare it to that theoretical solution of the Laplace equation by separation of variables. Over here on the left-hand side, I've depicted the particular problem in thermodynamics that I'm going to think about, the particular heat equation problem I'm going to think about. So I'm imagining some very large bath of cold water. And into that very large bath of cold water, I'm dropping a hot steel rod, initially at 100 degrees Celsius. I've arranged that the cylindrical walls of the steel rod are insulated with some insulating material, and only the left-hand end, the right-hand end cap, are exposed to the water. And so if we were to watch the temperature, measure the temperature in the steel rod along the length of the rod, we would see the steel rod cool, and it would cool from the ends working inwards. And we want to solve the heat equation to find out exactly how it cools as a function of time. So that's the basic problem. It's a problem where we've got both initial conditions and boundary conditions. The initial condition is that the steel rod initially is all at 100 degrees Celsius at time 0. Boundary conditions are that the two ends of the rod, left and right, are at all times going to be in contact with the water. They're going to be at 0 degrees Celsius at all times. And so there's both initial and boundary conditions in this particular problem. Over on the right-hand side, I sketched out my solution to this heat equation problem. And you probably noticed is rather similar to my solution to the Laplace's equation problem. And there are a lot of similarities in this problem, although there are some differences in this problem. So let's talk about the procedure for solving this problem. So upstairs here is the heat equation. I've used U to denote the temperature here. This U here is a function of space and time for the steel rod. It describes both the space dependence of the temperature of the steel rod and the time dependence of the temperature of the steel rod. It's a partial differential equation in U. First order differentials with respect to time, second order differentials with respect to space, and it contains this diffusion constant that determines this relative scale of the space and time dependence, how quickly or slowly the steel rod will cool down. So like in Laplace's equation, we made a hypothesis that that potential could be written as separate functions of x and y coordinates. In this case, we're going to make the hypothesis that the temperature can be written as separate functions of the space and time coordinates. And so I'm hypothesizing here that U can be written as a product of a function x, describing the spatial dependence of the temperature, and T describing the time dependence of the temperature. If I do that, I can break the single partial differential equation down into two ordinary differential equations, one describing the time dependence over here on the left, one describing the space dependence over here on the right-hand side. When I do that procedure, I introduce a constant, a separation constant. And for convenience, I've given that constant here the symbol alpha squared. So here's the separation constant alpha squared in the time differential equation. Here's the constant alpha squared in the space equation. And that's just the same as happened in the case of Laplace's equation. We introduced a separation constant when we pulled apart the x and the y space dependencies. Now, these are familiar differential equations. The one on the left says that the first differential of a function is in proportion to the function itself. The one on the right says that the second order differential of the function is in proportion to the function itself. And these have very familiar, well-known solutions to them. And therefore, at this moment, at this point, we can just write down the solution to U, the function of space and time, as a product of the solution to this time dependence and this space dependence. So we can write down this general solution here. And if you look at this general solution here, it's an enormous infinite family of solutions. It contains these space dependence. Here's the x's. It contains the time dependence. Here's the t's. It contains this separation parameter. This should be alpha, not beta. Alpha squared, not beta. And it contains a number of other arbitrary coefficients, the A1, the A2, B1, B2, that just correspond to this enormous family of solutions to this problem. Now the job is to apply the boundary conditions to pick out of this general infinite family of solutions the one solution for our particular problem. And that's what I've done here. I haven't given you any of the details, but it's just a matter of applying the fact that initially the temperature is 100 degrees Celsius everywhere, and also applying the fact that at the left-hand end of the rod, the right-hand end of the rod, the temperature is always, at all times, 0 degrees Celsius. That's sufficient to pick out of the solution, the general solution, this single solution here. So if you look at this single solution here, it contains a function of time, describing the time dependence, contains a function of x, describing the space dependence of the temperature. It contains the diffusion constant, of course, which is going to set the time scale for the rod cooling down. So we should expect to see that in the time dependence of the function. It contains the initial temperature, T naught. We should expect, of course, to see that in the solution. It tells us, if you look at the time dependence, it says that with time, the temperature of the rod is going to decrease towards 0. So this is controlling the time dependence of the solution and is going to drive the steel rod to the equilibrium temperature of the water bath. And then it contains the x dependence. of the temperature along the length of the steel rod. This is a summation of many sine waves, and it's a summation of many sine waves weighted in a way that the temperature at the left end and right end ends is always zero, but the temperature along the length of the rod, as it cools down, it kind of cools down unevenly. It cools down faster at the left-hand side than the right-hand side. The last thing to cool down is the center of the rod. And that's all embedded in this sum of sine waves here. And this looks very similar to the solution to Laplace's equation, the electrostatic problem. So in this graph, I'm plotting a solution to the heat equation for the long steel bar dropped into the water as a function of time. Horizontally, I've got the position along the length of the steel bar from 0 to 100 here. And then vertically, I'm plotting the temperature from 0 to 100 degrees Celsius. And then these different curves correspond to the temperature profile or the temperature gradient at different times. So in blue, after 1 second after I drop the steel bar into the water, orange after 10 seconds, green after 100 seconds, and so on to the magenta after 1,000 seconds. You see something, in a sense, we already knew, in a sense, something our intuition tells us. After just 1 second, well, some heat has flowed out from the far left and the far right of the steel bar. The far right and the far left have cooled down a little bit, but inside the body of the steel bar, it's still all at 100 degrees Celsius. It knows nothing about being dropped into a bath of cold water. As time goes on, after 10 seconds here in orange, more heat has flowed out of the left and right hand ends of the steel bar. The fact that the bar is immersed in cold water has been communicated deeper into the steel bar. And so you see a greater region of cooling on the left, a greater region of cooling on the right, but still in the center. If you're living in the center, you don't know that you're in the cold water yet. By 100 seconds, everything is cooling down. Every region of the steel bar, even the center, is cooling down. Now, the ends have cooled down much more than the center, but everybody's cooling down. After 500 seconds, everybody's cooled down a lot. And then finally, if we wait long enough, looks like 1,000 seconds is long enough, then the steel bar is reaching an equilibrium, which is where the entire length of the steel bar has cooled down to the temperature of the surrounding water bath.